Hello, good day. Due to this ongoing health crisis that we're experiencing, we will have to resort to online resources to facilitate our classes. One resource that I can use is the slide narration um, feature of Microsoft PowerPoint, which I will use for the next few lectures on BO-Savart law and Ampere's law. So pardon me as I navigate through the accessibility of this software because it's my first time doing a video lecture for Physics 72. Now, we were able to set up expressions to find the magnetic field due to a current carrying element. In particular, we were able to obtain the magnetic field due to, sorry for that, actually outside. So due to infinitesimal current carrying element. Now we will apply that formulation to straight line conductors, whatever we can apply that to, and generalize this expression as an integral, or as a summation of all contributions of infinitesimal current carrying elements. In particular, for this lecture, what we want to do is to find the magnetic field vector at any point in space due to a straight current carrying conductor. That's what we want to do. And of course, since we are dealing with vector fields, we can readily use the superposition principle to find the combination of vector fields in space. For example, if you have two current carrying wires, we can evaluate the contribution or the influence of these two current carrying wires by adding their the vector fields that they produce at any point in space. So that's what we will do, just like what we did for your electric field. Now, let's recall that Biot-Savart law is given by this equation. So for example, if you have here a current carrying wire, we can actually look at the contribution of each what do you call this, infinitesimal current carrying element, which is defined by its infinitesimal length vector dl. So in this case, if you have this current carrying wire, we can define the direction of this length vector, infinitesimal length vector, by locating the tangent, the tangent vector to that current carrying wire. Also, here, this r hat is defined as the unit vector, that is emanating from the source down to the field point that we are considering. So those vectors are essential in this formulation of your magnetic field, which is your Biot-Savart law. So this came from an infinitesimal formulation, and by doing an integration, we are actually adding all the dLs along this current carrying wire, effectively adding up all the contributions of each infinitesimal element at this field point. Of course, again, as I have mentioned or emphasized in class, the field point that you're considering will significantly alter the magnetic field that you will obtain. For example, if you consider a field point in this part of your space, it will be different when you are actually considering a field point somewhere here. So it is very important that you define your r hat correctly, because if you do not, if you fail to set up that r hat, most likely you will not get the correct answer. So of course, if you want to get the direction of your magnetic field, what you have to do is to do your right hand rules. That's the most important thing that you should do. So for example, for this expression, you have dl cross r hat, Like before, you just have to point your hand towards the direction of DL and curl your hand towards the direction of R hat. No? So you can do that at home. Okay? So we can apply this formulation of the Biot-Savart law to a magnetic field due to a straight wire. No? So ang meron tayo ngayon, we have an expression for the general case. No? So for example, if you have a straight wire, we ask what is the magnetic field at point P. No? Of course, what we have to identify first, no, is your dB, which is your infinitesimal magnetic field at the field point. In this case, the field point is this point, no, this point P, no, and the source point, no, are different DLs along this wire, no. So you can already see that we are actually adding the contributions along along the y-axis. Hence, most likely, the variable of integration is dy. But let us first consider each case. So for example, this one, if you have here an infinitesimal current carrying element dl here, no, we must find the, what do you call this, the direction, no, of the magnetic field at that point. So for here, of course, we can identify dl and r hat in this case. Dl, no, since our current is moving upwards towards the positive z-axis, we are sure that dl is also oriented in the positive z-axis, positive y-axis, sorry, because that's how we define the length vector. For our hat, of course, it is pointing from your infinitesimal current carrying element dl towards the field point P. No? So in this case, R hat, no, is the unit vector defining this R vector. No? So always remember that R hat is defined as your R vector divided by its magnitude. Okay, so that's how we define the unit vector R hat. No? So again, that's the first step. No? The first step is to identify the effect of each infinitesimal field element. No? The next step that we should do, of course, is to integrate that. No? We have to add up all the contributions of DL along the y-axis and along the length of the wire. Of course, we do not have to integrate over the whole thing, no, because for this example, no, it is only from negative A to A where we have a current that is flowing. No, beyond those values of y, there are no current sources. No, so there will be no contribution for those locations. No, so how do we set up this infinitesimal magnetic field? So the magnitude, no, the magnitude of this magnetic field. So for example, for this current carrying element dl, the magnitude of the magnetic field or the infinitesimal magnetic field at that point is given by IDL sine phi. It's IDL sine phi because it's a dl cross r hat, no? And the cross product between dl and r hat is just dl sine phi, where phi, no, is the angle between your what do you call this? It is the angle between your r hat and dl. Okay. So in this case, in this illustration, we can already see what the definition of phi is. No, phi is defined as the angle that is swept by your hand when you do your dl cross r hat. So for in this case, dl is pointed in the y direction, no, and your r hat is what do you call this? Let me do it. So for example, this one, no, if you do your right hand rule, no, from DL, which is pointing to the y direction, curl your hand towards the direction of your r hat, and you get what phi is. So in this case, phi is this angle, no, the angle between DL and r hat. No? Now, of course, to obtain sine phi, no, we have to write it down in terms of um, known values. What do I mean by known values? We know that the field point, no, is located x distance from the midpoint of the current carrying wire. Hence, we can define it using this distance, of course, sorry, this distance and this distance from the origin y. No? So in this case, here r is the distance between the field point and the source point, where x is the distance of the field point from the origin, no? And y is the distance of the current carrying element dl from the origin. No? So this is x and this is y. That's how we define this r equal to square root of x squared plus y squared. Sine phi in this case is actually defined as sine pi minus phi. Now we can, because of the periodicity of the function sine, we can define sine phi as some sine pi minus phi. So whatever is the sine of pi minus phi, that's also the sine of the sine value of phi. No? In this case, sine phi is just your opposite over hypotenuse. No? So in this case, the side of the right triangle opposite to pi minus phi is x. Hence, your sine phi is defined as x over r, or x over x, square root of x squared plus y squared. No? Now, since dl is along y, the magnitude, so this is what I was referring to a while ago. Now we are trying to obtain the contributions, no, of each infinitesimal line element along the current carrying wire. No? So here, since we are moving along the y direction, dl is just dy. No? Hence, giving us an infinitesimal magnetic field magnitude equal to mu naught I, no, over 4 pi x dy over x squared plus y squared raised to 3 halves. No? So, bakit x squared plus y squared raised to 3 halves? No? So remember, since your dB is mu naught over 4 pi IDL sine phi over r squared, your r squared gives you x squared plus y squared. No? However, there is an additional x over r here, which is your sine phi, while your dl is just equal to dy. No? So what you effectively get here is a mu naught, it's very hard to write equations here. It's mu naught over 4 pi multiplied by I, then your x dy over r cubed. No? However, your r is just the square root of x squared plus y squared, hence r cubed is just x squared plus y squared raised to 3 halves. No? So that's how we set up this equation. Now, now to obtain the, what do you call this, the overall contribution of this straight wire, what we have to do is to integrate this expression for dB from negative a to a. Now, why the hell are we integrating from negative a to a? No? Since we are actually adding up all dy's located from negative a to a, no? That is the reason why we are integrating from negative a to a over y. No? So um, the the sense of this integration setup, integration procedure is the same as what we are considering when we're evaluating the overall or the net electric field due to a charge distribution. No? So in the same way, dito naman, we have infinitesimal current elements. Okay? So if we let y to be equal to x tangent u, no? This is actually, what do you call this? Trigonometric substitution procedure. So if we let y to be equal to x tangent u, what we get is this form, no? Um, since this is a given integral, no? So if you do that, we obtain this, no? And if we evaluate this, what we get is a magnetic field magnitude equal to mu naught I over 2 pi multiplied by a over x over square root of x squared plus a squared. No? So that's the magnetic field due to a straight wire. No? Of course, we have we have always been interested with the infinite case, no? Because much of symmetry arguments rely on this infinite case. What do you call this? Infinite case consideration, no? So here, what we're doing is we are letting a to be much greater than x, no? So ang ginagawa natin dito, we are actually letting x or the field point approach, no? Approach the line charge, no? And in doing so, we are we are making this illusion, no? That as we go nearer and nearer the charged line element, no? Ang nangyayari, the wire suddenly appears as if it is infinite, no? So that's what we're doing here, in the same way as we did for your electric field calculations, no? So what happens when a is much larger than x? So if a is much larger than x, what we can do is to multiply 1 over a, no? We can multiply 1 over a to the numerator and the denominator to obtain this expression. Now, since a is much larger than x, what happens is that we can actually consider this, no, value as 0. So we are approximating in the linear sense. No? So hanggang linear term lang tayo because we are already taking out all contributions that are what do you call this, of order 2, no, squared and above. So if you have an x squared, an x cubed, so on and so forth, no, we are canceling that out because x over a is a very small value, no, it is much less than 1, no, which we have here as well. Okay, doing so, what we get is a magnetic field magnitude equal to mu naught I over 2 pi x, no? Where x is this distance, no? So imagine if you try to, so for example, this is your wire, no? So for example, this is your wire. If we try to calculate for the magnetic field around that wire, no? What you get is a magnitude of a magnetic field magnitude of mu naught I over 2 pi r, where r, no, is the radial distance from the axis. So for example, you measure a radius r, encircle about that wire with radius r, what you get is this roughly the same magnitude, which is just mu naught I over 2 pi r. Okay. So at all points in a circle of radius r, around a long straight current carrying wire, the magnitude B is just given by mu naught I over 2 pi r. So this is valid for all very long, or well, if we can consider infinitely long straight wires. Of course, we are avoiding the use of the term infinite, no, because uh, in in physical reality, we really do not have infinitely long wires. Instead, what we're considering here are very long straight wires. Okay. Now you can obtain the direction of your, what do you call this? Can obtain the direction of your current, no, using your right hand rule. No, what you need to do is to point your, so for example, this is your right hand. You need to point your thumb towards the direction of the current, no, and curl your hand. No, curl your hand. What do you call this? In this direction, no, to get the magnetic field direction for each point. For example, here as you move along, no, dito, if you measure the magnetic field, it's pointing in that way, and if you continue curling that in this direction, pag ganun naman yung magnetic field. And if you continue that, what you get is a complete visualization of your magnetic field line, no? Where in each point of your magnetic field line representation, you get what do you call this? A unique magnetic field vectors. For example, this one. No? So iba-iba yung direction ng magnetic field as you circle, no, around the wire. Now, so we have already applied the Biot-Savart law for, well, a fairly easy case, no? Because it's highly symmetric. We can easily obtain an expression for the magnetic field due to this line charge. How about yeah, there. Let us consider examples, of course. So for example, here we have three long straight conducting wires that each carry a current I in the direction shown. So for example, here current 1 and current 2 are pointed out of the page, and current 3 are pointed into the page. So here, what we want to do is to find the magnitude and direction of the resultant magnetic field at point P. Now, how can we obtain the magnetic field at point P? So of course, what we need to do first, no, is to identify the direction of the magnetic field for each case. No? So to do that, what you have to do is your right-hand rule. No? So for example, for wire 1, no? So for wire 2 first, no? You just have to what do you call this? Point your thumb towards the direction of the current element and curl your hand, no, like this, no, right, like corkscrew, no, and find that at point P the direction of the magnetic field is upwards, no, it's in the positive y direction, no. On the other hand, if we consider wire 3, no, so again, point your thumb towards the direction of the current, no, and curl your hand like a corkscrew and find that the magnetic field due to point 3 at point P is also upwards, no. And if again, if you do that for 1, no, in the same way, no, we find that the direction of the magnetic field due to lines currents 1, 2, and 3, no, are all in the same direction. No? So we just have to add the contributions of each wire, current carrying wire, using your superposition. No? So how do we do that? So again, for currents 1, 2, and 3, all of them are pointing upwards. No? So if you use the formula mu naught I over 2 pi r for B1, what you get is a mu naught I over 4 pi r. Remember that the distance of the field point to the source point is important. No? Here, for the first magnetic field contribution, no, which is contributed by wire 1, the distance is 2r. No? That's the reason why what you get for the magnetic field is mu naught I over 4 pi r. No? In the same way, we can do that for 2 and 3. Now, since wire 2 and 3 are equidistant from point P, which is at r, a distance r, no? What you get for the magnitude is mu naught I over 2 pi r and another mu naught I over 2 pi r. No? So that's how we obtain the magnitude of the magnetic field for each current carrying element at a certain point. No? So adding this up, what we get is a net magnetic field equal to 5 mu naught I over 4 pi r upwards. No? Or this gives us a what do you call this? A net magnetic field equal to 5 mu naught I over 4 pi r j hat. Next, we can consider another example in which we have what do you call this? Non-collinear. No? So they are not aligned in a linear array. We have here 4 wires that are located at the vertex, or what do you call this? The corners of a square. So you have here 4 long parallel power lines that each carry 100 ampere current. So this is the magnitude of your current I. Here we have a cross-sectional diagram of these lines. We have here a square, no? So these lines in their cross-section are actually in the corners of a square, no? That are of length 20 centimeters. 20 centimeters on each side. No? So here, what we want to do is to find the net magnetic field at the center of each square. Now, doing that, of course, we have to identify the what do you call this? The contribution of each wire at the center of the square, which is roughly in this position. No? So what are the important quantities that we have to calculate for? We need to know what the distance of this field point is to our sources. No? We can easily see that since we have a square, all of these lines are actually equidistant, no, to the center of the square. And that's why we call it the center, because it is equidistant to every corner of the square. So whatever we get for this r, no, applies for all r's as well. Now, however, the complicated part in this calculation is actually your direction. Now, we have to find the direction due to each current carrying wire, which we can do using your right-hand rule. No? So the important formula that we have to use for this calculation is your mu naught I over 2 pi r, since we are dealing with straight current carrying lines. No? So if we do your right-hand rule for each line, no, what you get here, for at least for wire 1 at first, is this one. No? So again, you just have to point your thumb towards the direction of your current. No? And if you do your right-hand screw rule, no, you find that the magnetic field at this point is towards this direction, no? Which is tangent. No? Always remember, it is tangent, no, this imaginary circle which your right-hand screw rule makes. Now that imaginary circle has a radius small r, which is the distance of your wire, no, to your field point. No? Now, if we do this procedure for the next wires, for example, wire 2, if you do your right-hand rule for wire 2, your wire 2 is along this direction, your current is flowing through this direction. No? If you do your right hand rule, you will find a vector that is pointing towards this direction. No? So it's actually a vector with the same magnitude, no, that is pointing opposite to wire 1, no, if we consider this axis. No? So with respect to this axis, they are pointing opposite each other. So you can see already that there are some components that will cancel out. No? So if we do this again for wire 3, what you get is some vector that is pointing in that direction. So do your right hand rule again. No? Tangent to that point P, or well, what do you call this? Tangent to the circle that your corkscrew makes, no, is some vector 3, B3, no, which is pointing opposite to wire 2. And lastly, your wire 4, which is pointed into the page. No? If you do your right hand rule, no? So if you do your right hand rule at point P, the direction of the magnetic field is in this way. No? Therefore, you have here a net magnetic field equal to 0. No? All the magnetic field contributions of each wire cancels out at that point, at the center. No? Well, of course, if you consider other points, points other than the center, you will get a non-zero magnetic field. No? But in this case, since we are considering a highly symmetric case, for example, in this one, no, this current, no, is course, what do you call this? Has another pair here, no, which is pointed, which has a magnetic field that points in the opposite direction as the other. No, parehas din for wire 3 and wire 2. They have contributions that are pointing opposite, not to each other. So due to symmetry, due to the high symmetry of the problem, the net magnetic field is equal to 0. So supposedly we should have this as our attendance quiz. However, we were not able to meet. So let us consider this problem. We have here two infinitely long wires, each carrying a current I as shown. No? We have to find the magnetic or the magnitude of the net magnetic field at point P. No? So how do we go about this problem? Again, the most crucial part is first to find the magnetic field direction. No, because finding the magnitude is an easy calculation, because you know that the magnetic field due to a current carrying wire is just mu naught I over 2 pi r. It just depends on the distance of the point that you are considering and the current that the wire is carrying. No? So if we consider this, no? So for example, for this, let us consider this. No? If we consider this left wire, which is pointing downwards, no? We can again point your thumb towards the direction of the current, no? And curl your hand like this, no? And find that the magnetic field at point P is actually pointing out of the page. No, you can do it yourself. So again, point your thumb towards the direction of your current carrying wire and curl your hand, no, like a corkscrew. And once you encounter, or well, once you touch that point P, look at the direction of the tip of your hand. No, what you get is a magnetic field that is pointing out of the page. No, now if we do that, if you do the same procedure for the right wire, what we get, so for example, this one, tapos you do your right hand rule, no? Papunta sa akin yung magnetic field. Hence, also in the same way, your magnetic field is also out of the page. So here we can already see that since they are equidistant from each other, they will just add up. Also, the direction of the magnetic field is the same for each wire, so they will just add up. No? Same direction, you just have to add the magnetic field magnitude. No? The magnitude of the magnetic field is of course just equal to mu naught I over pi a, I mean, since it's just mu naught I over 2 pi a for the wire 1 and mu naught I over 2 pi a for wire 2. Adding the two together, you get mu naught I over pi a. No? Um, therefore, it gives us, well, therefore it gives us, oops, a magnetic field magnitude equal to mu naught I over pi a out of the page. Or, well, if you set your z direction to be out of the page, you get a mu naught I over pi a z hat. No? Now, since we already know the magnetic field due to a current carrying wire, the next step is of course to find the interactions. No? We have to find how two wires interact with each other. No? And that we will be able to get, no, by using your formula for the force, no, due to a current carrying wire. Now, since we already have a magnitude, well, of course, an expression for the magnetic field due to a current carrying wire, and we already know how a current carrying wire interacts with the magnetic field, we can combine the two, no, to find the force between two parallel conductors. Well, in this case, we will be considering two or more parallel wires. No? So, for this part of the lecture, we will consider the force per unit length on a current carrying wire due to the magnetic field produced by other current carrying wires. Now, why is it important that we must consider the force per unit length? So, unahan ko na. The reason why we are looking at the force per unit length is because the formula that we obtained for the current carrying wire, no, is for an infinitely or a very long wire. No? Therefore, no, if we do not consider a force per unit length, what we get is an L, diba? Your force is equal to IL cross B. No? That L, if the wire is infinitely long, becomes infinitely large. Hence, you will get a force that is infinitely large. But that's not the case. That's not how we are analyzing the problem. No, we are analyzing the problem locally. No, hence we are considering a force per unit length in this case. No, now. So you can imagine this in this way, no? If you have infinitely long wires, no, and consider the interaction of each segment of those wires, no, interaction. For example, this is a segment of wire 1, this is a segment of wire 2, and add them together, no, over the whole length. Given that it is infinitely long, no, what you get is an infinitely large force. No? So in our analysis, it is only the only useful quantity for us, of course, is to find the force per unit length. Okay? Okay. So now let us proceed to this calculation. So, well, what we did back then is to consider the interaction between two point particles. No? So again, there are two parts in magnetic interactions. No? We have a moving charge that produces a magnetic field, right? And that magnetic field then interacts with another moving charge, no, and exerts a force, no, that is perpendicular, no, mutually perpendicular to the magnetic field due to the other charge, no, and the velocity of your what do you call this? The field, well, what do you call this? The velocity of the particle that you are considering. Now, so for example, you have a source charge in a field, let's call it a field charge. That field charge is moving in some direction, no, due to the magnetic field produced by the source charge, no, the field charge will be or will feel a force, no, that is mutually perpendicular to its velocity and the magnetic field due to the source charge, much like how it is illustrated in this diagram. So, kita nyo dito, the magnetic field due to this source, no, is this B, no, and the force exerted by that magnetic field is in the direction of V cross B, no, which you can obtain by doing your right hand rule. Now we can generalize this interaction. Well, of course, your current, no, diba? Your current is just a group of charges that are moving along a line. No, imagine if you have a straight current carrying wire. No, you can generalize that. Well, what do you call this? We can characterize, no, a uh, straight line wire that is carrying a current, no, as a group of moving charges, no, with the same drift velocity, no. Ganun yung analysis in this case, no. So we generalize that to the interaction between parallel wires. No. Why are we considering parallel wires, you say? Of course, parallel wires, no, will not meet. That's the analysis that we want to employ in this case. No? Okay, let us proceed. So here, you can actually consider cases. No? In this case, the upper wire, or the what do you call this? The lower wire produces a magnetic field that at the position of the magnetic wire has magnitude mu naught I over 2 pi r. No? Here, r is this distance. No? No? And I is the magnitude of this current. No? So that's the magnitude of the magnetic field at this point. No? Now, how do you get the what do you call this? The direction of the magnetic field? You just have to do your right hand rule. You point your thumb in the direction of the current and curl your hand, no, in the direction well, using your right hand screw rule. No? So the magnetic force, no, can then be obtained using your I prime L cross B. Now, why are we using I prime? It's I prime because we are considering the force in the upper conductor. No? So here, the source of the magnetic field is the lower conductor. So this is the source. Okay. Yeah, shit. So this is the source, while the what do you call this? The field current carrying wire is this one, yung prime. No? So in this case, your source is the unprimed current, and the field point that you are observing in is the primed, no, current. No? So para lang madaling matandaan. No? So if you do your I prime L cross B, in this case, no, the magnetic field due to I, no, produces a magnitude of mu naught I over 2 pi r and a direction that is out of the page. So how do you do that? Again, point your thumb towards the direction of the current, then curl. If you do your corkscrew rule, no, the direction will be out of the page towards you. No? So that's how you get this. Therefore, the magnetic force experienced by this segment L, etong segment na to, due to the magnetic field produced by this current carrying element is given by ILB, where B is just given by mu naught I over 2 pi r. No? Therefore, the magnitude is simply mu naught I prime times L over 2 pi r. However, we are considering a force per unit length analysis. No? Therefore, the magnitude of your force per unit length, so the magnitude of your force per unit length is mu naught I prime over 2 pi r. Okay? Now, if we do the same analysis, no, for this case, no, so ang nangyari naman, the source of the magnetic field is the upper conductor, no. So the source, this is the source in this case. So this is your case 2. So case 2, this is the source of the magnetic field, and this is the field point or the observation point. No, this is we are trying to measure the force per unit length exerted on the lower conductor by the upper conductor. No. Now, if you do your right hand rule for I prime, no, the direction of the magnetic field at the position of the lower conductor, no, is into the page. No? So, again, you have to do your right hand rule. Point your thumb towards this direction. No? Tapos, i-curl nyo yung kamay nyo. And you will see that at the position of the wire, no, the current is, the magnetic field is pointing into the page. No? Hence, what you get is a magnitude of mu naught I over 2 pi r that is into the page. No? Therefore, the magnetic force exerted by the segment having length L on the lower conductor is IL cross B, which has a magnitude of ILB. Here, the, what do you call this? The current that we are, what do you call this? So in this case, the magnetic field is exerting, the magnetic field due to I prime is exerting a force on the current I. No? Kaya ILB. So it becomes mu naught I prime over 2 pi r times L. No? The direction of which is upward. No? Why is it upward? Your L is pointing, so your L is pointing in this direction, while your magnetic field is toward, so this is your L, this is your B. Therefore, if you curl your hand, no, with L cross B, what you get is an upward direction. No? In the same way as you do for your for the other case. No? So we can generalize this in this manner. What you get is our forces, no, that are actually opposite to each other. Therefore, if you have two current carrying wires, no, in which their currents are pointing in the same direction, no, if we have that, no, the force between them are actually attractive. No? So I prime exerts a force that is upwards, no, on I, while I exerts a force that is downward, no, on I prime. Okay? With magnitude equal to mu naught I prime over 2 pi r. So in conclusion, interestingly, two long parallel current carrying conductors attract if the currents are in the same direction. So kapag parehas na pag ganun yung current, no, they will attract each other. No? Now, is Newton's third law obeyed? Of course, yes. No? Whatever the force between them, no, are opposite. Well, they are force pairs, no, that are exerted opposite to each other. No? So the action of the other is an opposite and equal reaction by another. No? So dito naman, if we have two current carrying conductors that are pointing in the opposite direction, they will repel each other. You can do the same analysis as we did before, no? And you will see that um, if the currents are opposite each other, they will repel. Again, is Newton's third law obeyed? Yes. No? So yeah. So the force per unit length is therefore given by mu naught I prime over 2 pi r, where r is the distance between the two wires. Again, we are considering a force per unit length because our formulation of the magnetic field is due to very long conductors. No? So we are only interested in finding the effect on what do you call this, a segment of length L, no, on the other wires. For example, if you have a current carrying wire, no, that is producing a magnetic field, and let another current carrying wire in the vicinity, or put it in the vicinity of the magnetic field producing wire, no, you can get the force per unit length, no, meaning the force exerted on a length of that upper conductor, no, which is equal to mu naught I prime over 2 pi r. Now this force per unit length is of course applicable only for two long parallel conductors, current carrying conductors. Okay, so this is a concept test. So let's just what do you call this? Let's just what do you call this? Explain why the answer is FW1 equal to F negative FW2. So here we have two parallel wires that are lying on the floor and carry identical currents in the same direction. Now, if the current in W1 is increased by a factor of 2, which of the following relations about the magnetic force acting on each wire is true? So again, if we do not use, well, do not use any calculations of all sorts, no, we can already invoke that Newton's third law must be obeyed for this case. Hence, whatever the force is exerted by wire 1 will be opposite to that of the force exerted by wire 2 on wire 1. No? However, if you try to calculate for the force exerted by one on another, no, you will see that they will have an equal magnitude, right? Because the magnitude is just mu naught I1 due to W1 times I2 due to W2 over um, over 2 pi r, where r is the distance between the two, no? So wala namang pinagkaiba yung magnitude. However, no, the direction is always opposite, no, the force exerted by one wire on another. So whatever the force is exerted by the wire 1 on wire 2 is opposite the direction of that exerted by wire 2 on wire 1. No? That's why the answer is letter B. If we have here two long parallel wires, no? First, let us first answer this question. Is the force attractive or repulsive? Since we have two wires that are flowing in the opposite direction, no, with respect to each other, no, we know that the force is repulsive, no? So yun yung una nating ano. Remember that if they are in the same direction, the force is attractive. If they are flowing in opposite directions, the force is repulsive, no? Now, the magnitude of the force can be easily obtained. No, that's just mu naught I prime over 2 pi r. We know the distance of the wires. We know it to be 0.4 meters. No, we know the current magnitude, that's 5 amperes and 2 amperes. So to get the force per unit, so in this case, we can do, what do you call this? The length that we are considering is just 1.2 meters. No, so you just have to, of course, multiply this. So mu naught over 2 pi is just 2 times 10 to the negative 7. I1 is equal to 5 amperes. I2 is equal to 2 amperes. The length that we are considering is just 1.2 meters over the distance between the two, which is 0.4 meters. If you do the calculation, you just have here 12 times 2, that's 24, divided by 0.4. I know, you have 10 times 1.2, that's 12, times 2, that's 24, times 10 to the negative 7, divided by 0.4, yeah, you get 6 times 10 to the negative 6 newtons. No? So, of course, the force is repulsive since the currents are in opposite directions. Okay? Another example is this one. So here you have three wires. No, wire X is flowing to the right, wire Y is flowing to the left, and wire Z is flowing to the left, to the right. I mean, sorry. So here our question is, what is the direction of the magnetic force experienced by wire Z due to wires X and Y? Now, how do we solve this? So the direction of the force on Z due to X is upward. No? So of course, X and Y are flowing in the same direction. Therefore, the force between them is attractive, right? Now, due to Y, since they are in the opposite direction, the force is repulsive. No? Magkakatalo na lang tayo dun sa distance, no? On Z. Obviously, X is, what do you call this? X is farther than Y by a distance D. Kasi the distance between Y and Z is just D, while the distance between X and Z is 2D. So, if you add the two, of course, one will overcome the other. The magnitude, so sige, actually not. If you consider this, no, so for this case, so X and Z are attractive. Therefore, the force in Z is upwards. No? For Y and Z, no, the force, yeah, of course, yeah, tama. Okay. The force magnitude is just equal to mu naught I prime over 2 pi r times IL. No? Now, since Y is closer to Z, no, because of this inversely proportional relation to the distance, F is approximately just 1 over R. No? The magnitude of the force due to Y, no, is greater than that exerted by X. No? So if that's the case, the net force direction is of course the same as that of Y, no? Which is downward. No? Mas malayo yung X, therefore the force of X on Z is weaker than that of the force of Y exerted on Z. No? So the answer is downward. Okay? For the last exercise, no? The last example for this lecture, we have here two long parallel wires that are separated by a distance of 2.5 centimeters. The force per unit length that each wire exerts on the force is 4 times 10 to the negative 5 Newton per meter. No? It's a force per unit length. And the wires repel each other. No. So what can we get from the given? No? We know that distance is 2.5 centimeters. Therefore, R is equal to 2.5. The force per unit length is 4. So the left-hand side is 4 times 10 to the negative 5. The wires repel each other. Therefore, we know that the direction of each of the wires relative to each other are opposite. No? So whatever the direction of wire 1 is opposite the direction of wire 2. Now, what we want to find is the current in the second wire and the direction, no? Since alam na natin yung relationship na if they repel each other, we are sure that they are pointing in opposite directions, no? So ang kailangan na natin kunin ay yung letter A. What is the current in the second wire? Now we can do that calculation by, of course, using your force per unit length, no? We know the force per unit length to be 4 times 10 to the negative 5. So that's this one, no? Now we just have to multiply that force per unit length by 2 pi r over mu naught I1, no? Since gusto nating i-isolate yung I2. Okay? Doing that calculation, what we get is some 8.33 amperes. No? It's an easy calculation. You just have to input it in your calculator. So again, ayun nga, since our analysis tells us that two wires that carry opposite, currents that are flowing in the opposite direction, no, actually repel each other, no, may answer na agad tayo for letter B. They are opposite. They are flowing in opposite directions. Okay. So in this lecture, we have already obtained the magnetic field due to a straight wire, no? And we were able to obtain the force per unit length. No? So if you have two or more wires, we can already obtain the interaction, no, between those wires. No? So that's the end of this lecture. The next lecture will be on circular loops. Okay, so thank you.